All right, in this video, we are going to talk about reaction mechanisms, basically the step-by-step process that explains how we get from reactants to products. How does the reaction actually occur in a step-by-step process? Okay, so this is kind of an abstract concept. If you ever take organic chemistry, this comes up all the time. For right now, it's just gonna seem a little weird, but we'll be all right. So it's basically a series of steps that explains how reactants become products. Oops, products. Okay. Here is an example of what it looks like in organic chemistry. I'm just going to label this as organic chemistry. The organic chemistry version is not what our version is going to look like, and that's okay. So in organic chemistry, we use this shorthand where basically we have a bunch of carbon-carbon bonds. So if we had something like this, what this means is we have a carbon connected to another carbon, and then this is a double bond to another carbon. And and carbons always have 4 bonds, so however many hydrogens you need to make it have 4 bonds. So we have 1, 2, 3 hydrogens here, 1 hydrogen there, because that would be 4 bonds, and then we have 2 hydrogens here. Doesn't really matter because we're ignoring the hydrogens anyway. In organic chemistry, what you would do is you would provide this with another reactant. In organic chemistry, the way it works is it's always something negative attacking something positive. So this double bond is made out of electrons. Electrons are negative, and between a hydrogen and a bromine, hydrogen's pretty positive and bromine's pretty negative. So this double bond, the electrons from that will attack the hydrogen, which will break this bond. Okay. And we end up forming, the hydrogen will stick at the end, and we end up forming a positive charge on that middle carbon. I'm drawing it in a circle because otherwise it's kind of hard to see. And then this bromine, which got kicked off with the electrons, now has a negative charge, and now negative attacks positive. So essentially what happens is the double bond vanishes and gets replaced by a hydrogen on the end of the chain and the bromine in the middle of the chain. Okay? This is what organic chemistry mechanisms look like. We are more worried about the rate law side of things. Okay? So when we talk about a mechanism, we have to, whatever we come up with, whatever step-by-step process it has to agree with the rate law. It also must agree with the stoichiometry of the reaction. So agree with stoichiometry. So what I'm saying is, if you looked at this reaction up here and it says, okay, for one of these molecules, you get one of these molecules. So you need one of these and one of these to get to here. That agrees with the stoichiometry. We don't have any information about the rate law yet, but whatever. Okay. If your stoichiometry said, oh, well, for every one of these, you're going to need 2 of these, and this is your mechanism is wrong because it doesn't agree with the stoichiometry. But both of these things have to be accounted for. It's kind of a big deal. Okay. Each of the individual steps are called elementary steps. I'm from New York, so if you hear me, I'm not from New York, so if you accidentally hear me say elementary, it's the same word, sorry. So the individual steps of a mechanism are called elementary steps or elementary steps. Okay. And there are a few assumptions that we can make about the elementary steps that make this part pretty easy. For the elementary steps, we're assuming that if you have like a balanced equation, the coefficients in the front are your exponents in your rate law. We assume the coefficients are the exponents of the rate law. We also assume that every individual step is reversible. Okay. That second one won't matter a whole lot most of the time, but we're going to at least account for it. Okay, so what that would mean for us is this reaction, because we have one of these and one of these, the rate law would be rate equals K times whatever this formula is raised to the 1, and this HBr raised to the 1. Because there's one of each, the coefficients just become the exponents, and you don't have to go through all the other legwork that we normally do for rate laws. Okay, so it does save some time and effort to think about the individual steps like this, but the assumption usually is okay. Okay. There is also something called a rate determining step. And the idea is if you have multiple steps in a reaction, usually the difference in speed between the fast step and the slow step is like tens of thousands of like orders of magnitude. Okay, so it's not like, oh, this one is 5% faster. It's usually like 50 billion times faster. So usually, whatever the slowest step is in the mechanism, we can assume that that is the rate of the overall reaction. So if there's like 3 elementary steps, the slowest of those 3, whatever the rate of that slow step is, we're going to assume that's the rate of the overall reaction. So the slowest step in mechanism determines the overall rate of the reaction. Okay. So let's look at an example and see how to actually like use any of this information, because right now it just all seems like gibberish probably, and that's okay. We'll get through it. Sorry, trying to get organized here. So let's look at an example of a proposed mechanism. So coming up with reaction mechanisms is kind of a really difficult process. I'm not expecting you to ever come up with a mechanism. I'm just asking you to analyze what's going on in the reaction. So let's say we've got this mechanism. It's a slow step and followed by a fast step. And the first step is that H2O2 reacts with iodine with a -1 charge. And what happens is basically it steals one of the oxygens. So we end up with H2O and OI minus. Okay. The fast step then turns around and, well, the whole thing starts again, and we have H2O2 reacting with this OI minus, and we form water and oxygen and I minus. This is the proposed mechanism for this reaction. So if you are given a mechanism, there's a couple ways we can think through this. Okay, or a couple things that we should be able to get out of this. Okay, so one thing is, what is the overall reaction? So typically what we do is we write all the reactants on one side and all the products on the other side, and anything that's the same on both sides, we cancel it out. So we have 2 different H2O2s on the left, so I'm going to write 2 H2O2. We also have an I minus and an OI minus on the left side of, so between both reactions we have this much stuff on the left, the reactant side. On the product side we have 2 waters, an O2, an OI minus, and an I minus. Okay, now what we do is anything that is exactly the same on both sides, we cancel it out. So we have an I minus here and an I minus there, we can cancel that out. We have an OI minus here and an OI minus here, we can cancel that out. This is 2 H2O2, we don't have any H2O2s over here. This is 2 H2Os, we don't have H2Os over here. This is O2, we don't have O2s over there. Okay, so this, whatever's left, is the overall reaction. So the answer would be 2 H2O2 forms 2 H2O plus oxygen. Okay? Yay, we did a good job. Okay, the next thing that we would be able to do is to identify any catalysts or intermediates. I'm going to need to define both of those things. Okay, so let me define both of these before we get too far in this process. Okay, a catalyst is something that speeds up a reaction. That is the easy answer as to what it is. But it is also something that is used up in the beginning and then you get it back at the end. It's almost like it gets used and recycled and then spit back out. So basically it gets used and reformed. Okay? So in other words, it's going to be both a reactant and a product. Okay, an intermediate, which I guess I'll do in a different color, an intermediate is not a reactant or a product. It's something that it forms along the way. Okay, so it's not a reactant or product. But gets formed along the way. Oops, along the way. I'm supposed to say along, sorry, can't spell. So, either the catalyst or the intermediate is going to be one of the things that we crossed out, okay? Not every reaction has a catalyst and not every reaction has an intermediate, but if it does have one, this is the process we would go through to figure it out. So, if we look at this overall reaction, we see that in the beginning, so we're only looking, the options are either I or OI minus. So I minus or OI minus. Those are our, it's either, they're either both catalysts, both intermediates, or one's a catalyst, one's an intermediate, but they're gonna be one of these things. Anything that gets crossed out is one of these categories, okay? So if we look at iodine, it was here in the beginning, it got used up to perform OI minus, and then we get it back at the end. So that sounds like a catalyst to me. It's both a reactant and a product. It got used and then it was reformed at the end. So I minus is our catalyst. Okay. As far as intermediates, if we look at OI minus, it was not here in the beginning and it's not here at the end, but it did form along the way and then it gets used up before the end. So that sounds like an intermediate to me. Okay, but it will always be one of these ones that's crossed out, and you will not always have a catalyst or it won't necessarily always have a catalyst, or you won't necessarily always have an intermediate, but this is how you would identify them if you do have them. This one obviously has both because I'm trying to explain the concept. And then the other thing we need to be able to do is to draw that reaction profile, like the curve from reaction to product with the activation energy in there. Let's kind of talk through how to do that. Okay. Well, a couple rules that are going to pop up here is however many steps you have, that's how many peaks you're going to have. You would also need to know if it's exothermic or endothermic, which I haven't told you yet, so I guess I'll go ahead and put it in here. Let's say it's exothermic, because I'm pretty sure it is. Okay. If it's exothermic, the products are going to be more stable than the reactants. That part is the same as what we saw before. Okay. The slow step is always the tallest peak, and the fast step is always the shorter of the two peaks, but both peaks are higher in energy than either the reactants or the products. So let's try to draw this thing. In an ideal world, I would be able to show you this at the same time as this, but I can't fit it both on here. So energy versus reaction progress. I'm just going to abbreviate that as reaction. Okay. Well, from our overall reaction, we have 2H2O2 as our reactants, and we also have iodine as a catalyst. So that's our starting materials. So 2H2O2 and I minus. That's our reactants. Sorry. Okay. Our first step is the slow step, so that's going to be the taller of the two peaks. And then we have to have a second peak. And then our products are going to be lower than our reactants because it's exothermic. Okay, so slow step, then fast step, which is why we have tall peak, followed by lower peak. If these were switched, these would switch. Okay? So, the products here are 2H2O and an O2, and we also get the I minus back. Yes, we canceled it out, but our overall reaction, we have I minus in the beginning, and we have I minus at the end. The catalyst is there as a reactant and a product. Okay? So, basically, it's 2H2O plus O2 plus I minus. This is one of the ways you can tell it's a catalyst, is it's there in the beginning and at the end. Okay? This little middle bit where it dips down, it's more stable than these like transition states, but it's not as stable as the reactants. This is where your intermediate lives. So basically, after the first slow step, we end up forming OI minus, and it gets used up before the products. So this is where the intermediate lives. So your intermediate will only exist in that middle range. Okay. On a quiz or exam, I might ask you to label the activation energy. So what you do is it's the difference between the reactant energy and the tallest peak. And you just label it E sub A. I might also ask you to label the delta H. It's literally the difference between the reactants and products. And that would be delta H. Okay? And because our products are lower than our reactants, delta H would be negative for this. Okay? The tallest peak, that is our least stable transition state. Okay? Technically, this is a transition state too, but it is more stable than that one. Okay? And the reason this is the slow step is that the reason this is the highest activation energy is this is the slow step. It's the one that has the most of the biggest barrier to overcome, which is why it's taking the longest time to get through. So in other words, we have a really slow step followed by a faster step, which is what we've got here, which makes sense with this. Okay. Yeah, it's a little messy, but it's kind of it's not too terrible here. All right, thanks.